Okay, so this is lecture 19. So today we're just going to be talking about positive recurrent and null recurrent. So this is something that only occurs when the state space is infinite. Okay, so just to motivate these two definitions, let's just recall something. Right, so recall for finite S, for finite state space S. And what we know is that there will always exist at least one stationary distribution, right? So there exists at least one stationary distribution or invariant distribution. Right? So we also actually just proved this fact. This was during the proof when we were trying to prove that the expected so we proved this. So we proved it. We proved this. This when just jog your memory when we were proving. Can you guys recall where do we prove this statement? So we did this in class. It's part of the other proof. So there is at least one. So this happened like we proved this when we were just proving the following fact, right? So pi of x is equal to the expectation. 1 over, I should say, 1 over the expectation of tx given the chain starts at x, right? So we did a rigorous proof for this formula in the class, and for the first step of this was just proving it would imply this result. So we construct something explicitly, and we show that it's actually a stationary distribution throughout the other proof. Okay. So now so when S is countably infinite, so for countable S that is not finite, so this statement here is no longer true, right? So this is no longer true. This fails. You can think about this fails, and it fails in two different ways. Fails in two different ways. And maybe I'll tell you in which sense it fails in two different ways, right? So recall the stationary distribution. The stationary distribution. So let's say so the stationary, any stationary distribution should satisfy the following two properties, right? Satisfies. The first one is it has satisfied this equality pi of p is equal to pi. And the second condition is that the pi has to be a probability measure. So these are the two conditions. So next, I'll just show you guys in different cases how would this fail, right? Okay, maybe I'll just say it now. So when we say it fails in two different ways, so you can think about the first way is that the only solution to this equation inside the first point is just the zero solution. This is like because pi equal to 0 will always be a solution to this equation in first one, right? So you can think about this as the first way of failing. It's like the worst case. And the second case that there actually exists non-zero solutions for this equation, but then they're not probability measure. So you can think about this as the second way. It's a second way to failing. Okay. So any questions so far? This is something that we have done previously. So essentially just recalling the definition of stationary distribution. Okay. So next, let's look at two different cases. So in this case, the first one, let's say if the irreducible Markov chain is transient, right? So here we just assume irreducible so that it's simple. I can talk about the entire Markov chain being transient or recurrent, right? Or else it's really it's just a simple way of saying the statement. So we just work with irreducible Markov chain. So if the Markov chain is transient, then there are two ways that this can fail. So either, so I'll just write. So there could be no non-zero solution. For pi of p is equal to pi, or there exists non-zero solution there's non-zero solutions, but pi is not a probability measure. So this is the case when it's transient. So essentially, we know when as long as the Markov chain is transient, then there is just no stationary distribution, and it fails in these two ways, right? Either there's no non-zero solution, or there exists non-zero solution, but it's not a probability measure. So now let's look at some examples for these cases. I guess the second case is simpler, because a simple example for the second case, we just have to look at simple symmetric walk on Z where P is not a half, right? So example, this is non-zero solution exists, but not probability measure, but not a probability measure. So you can think about there's no way to reduce this vector pi into a probability measure. Okay, so look at simple random walk on Z. It's one dimension where P is not a half. P is not a half, right? So in this case, it's an irreducible Markov chain and it's a transient. So we didn't prove it's transient in the class, but this is the first problem in your homework set, homework 3, right? So maybe I'll just draw the picture and then recall. So our chain basically just looks like this. So our state space is Z, and the chain will just jump to the right with probably P, and then jump to the left with probably 1 minus P, where P is not a half. Right? So now we want to solve the equation pi of P is equal to pi. So in this case, I'll just write down the P. Okay, I'll just write what the matrix P would look like, right? Well, first thing we can observe that the matrix P will just have all the zeros on the diagonal, right? Well, it's an infinite matrix, so it's not a matrix, so it just have zeros on the diagonal. And I'll ask you guys this. So on the what's going to be the number that is to the right of 0 for any of these zeros? What would be the number to the right of zeros in this matrix? It's P, right? Right? Because if you think about, let's say this row here, let's index this by I. Let's say this is the ith row. Okay, let me use a color chalk. Okay, hopefully the orange is going to show. Right, so think about if the orange one is the ith row, and then 0, this will also be the ith column, right? Then this is also I, and this is I. Right, so the transition from I to I is going to be 0, and the transition from I to I plus 1, right? So the next one is, of course, going to be I plus 1, right? I plus 1, and this is I minus 1, right? This is I. So with probability P, we go to I plus 1, and with probability 1 minus P, we go to 1 sorry, we go to I minus 1, right? And then it's the same thing happens here. So this is also P, this is 1 minus P, right? Okay, maybe this is a little bit too messy. So I'll just rewrite this entire matrix and then I'll just write in this way. So, so this is an infinite matrix where on the diagonal, we just have zeros. And on the upper diagonal, we just have P. And on the lower diagonal, we just have 1 minus P. Right? And then the rest are just 0. So this is basically the transition matrix in this case. Well, it's not really a matrix. So now let's look at what happens if we do the calculation pi of P is equal to pi. So pi of P is equal to pi. So, well, in this case, instead of just looking at the entire vector, let's just look at the ith coordinate. So let's say look at the ith coordinate, and also let's look at the ith coordinate of this vector here, right? So I'll draw the picture here on the bottom. Okay, so first let's write down the P here. Well, since we're only looking at the ith coordinate, so let's just say this is I, this is I. Okay, ignore these ones. So with this I, there's a 0 here, and then we have a P, a 1 minus P, and in the row above we have a 0 here, we have a P here, and then on the bottom row we have a 0 here, we have 1 minus P here, right? And this is the 0th row, and this is the 0th column, right? Okay. So now, okay, maybe I should write it this way. So this is I of P, the ith coordinate here. Okay. So now we want to multiply it by pi, which is here. Okay. So just for this one here, if we look at the ith coordinate, then we just have to multiply this vector pi here with the ith column, right? So this is essentially how the matrix multiplication works. Right? So we are just going to multiply. It's an inner product between pi and this ith column here, right? And this will give us the sure, I'll just write it this way. And then the inner product of these two will give us, by this equality here, this has to equal to pi I. Because you can think about the top here is pi multiplied by P. And then if we look at the ith column, it's just going to be this horizontal vector inner product with this vertical vector, right? Or dot product, inner product. Well, in this case, it will be infinite, but it's fine. Most of these are 0. And it's equal to pi I, so it has to equal to this one, right? So maybe I'll give you guys a minute. So can you write down this equality just turn this one into a precise equality? Right, just think about what happens if I do this inner product here. On the other side, I already know it's pi I, right? So we already know that. Okay. So it's on this side, we already know it's pi I. So I'll just write it this way. Okay, so pi I is coming from here, and then what's the expression that appears on the other side, which is essentially coming from the inner product. Anyone? Okay. Yeah. P times pi of I minus 1. Yeah, exactly. Right? So you can think about, so this part, it's just going to be coming from doing the inner product this side, and this side is just going to be this pi I here, right? Or yeah, I don't, yeah, maybe let's just say this. I'll just write it this way, right? Right. And then this inner product is just this, right? Coming from this, and from here we're going to get this side. I'll just write this way. Okay. Yeah. Right, so the pi here is not unique. So we're just trying to solve this system, pi of P is equal to pi, and then see what we get, right? So now if we have this equation here, so what's going to be a simple solution to this? Yeah, exactly. right? So in this case, we see that, so for, this is the linear difference equation, right? For pi of I is equal to P times pi I minus 1 plus 1 minus P to the pi I plus 1. And well, in this case, we don't really have any initial conditions, right? Because it's really an infinite vector. An observation we can make is that pi is equal to just an infinite array of constants. C is a solution, is a non-zero solution. Right? But then we see that there's no way for us to normalize this pi to be a probability measure, right? And but there is no way to normalize pi to a probability measure. And of course, by normalize, what I meant is just normally what you do is you just sum up all of these. I mean, if it's not constant, if it's something else, you can sum up all the entries of pi. And if it's something finite, you just divide pi by that number. So that just turns it into a probability measure, right? So all we need is just for them to sum up to be 1. Okay, maybe if I want to do a little bit more precise. Okay, yeah, that's all. Yeah.
There is no way to normalize the pi to probability measure. That means the pi cannot be like sigma LG.
No. Here it just means that if we sum up the entries of pi, it cannot be equal to 1.
Oh, so the sum of the pi.
Right. Yeah. Yes. Right. So that's in general, like if we write a probability measure as a vector, we just want the entries sum up to be 1. The non-negative entries sum up to be 1. But in this case, if they're all constant, there's no way for us to do that, right? Because normally what we do is we just divide by the sum of these entries, provided it's finite. Right? Okay. And so this is the first example. And of course, the second example would be we will write a Markov chain where there's just simply no non-zero solution, right? So this finished the first example. So the second example, I should change. Oh, I forgot to change the camera. Okay, I guess it's. Let's see this side. Okay, yeah, I guess this time is fine. They didn't miss much. Okay, so example 2. So in this case, there's just simply no non-zero solution to our equation pi of p is equal to pi. Okay. So I guess this Markov chain is not that complicated, but it's something that we don't really see often. So over here, let qi just be a sequence of numbers with, let's say, ri is equal to 1 minus qi, where so we require just the summation of ri, I goes from 1 to infinity, to be strictly less than 1. Right? So you can think about qi is going to be a sequence that is going to 1, and ri is a sequence that is going to be 0. For now, okay, we can also just assume all the ri's are positive, but I don't think we need it in the proof. So we can just keep this on the back of our mind. So over here, think about ri goes to 0. 0 as I goes to infinity. And then, of course, then qi goes to 1. 1 as I goes to infinity. Right? So you can think about this as what happens. Okay. So now to define a Markov chain, we're just going to write out the transition probability. So define a Markov chain on, in this case, let's say the non-negative integers, z plus 0, with the following transition probabilities. transition probability is also very simple. So the probability that we go, so from 0, we just go to 1 with probability 1. And we can also call this Q0, right? Over here, the general I goes from 1 to infinity. Right? There's no Q0. Let's just call Q0 to be 1. It's not important. And then for the rest, let's just do P of I to I plus 1. This has probability Qi. So with very high probability, the chain will march forward. And then the transition probability P also from I to 0, this is equal to Ri. Right? So essentially, the chain will just keep going up, up, up. And there will be a chance for it to return to 0, jump right away to 0. Right? So maybe to draw a picture. So we start here. I'll just draw a picture here. The 0, 1, 2, 3, 4. And then from 0, we go to 1 with probability 1. From 1 to 2, we go to with probability, I think it's the Q, Q1, Q1. And then this is Q2. This is Q3. And then from each place, and then we can jump back to 0, right? From 1, we jump up with R1. From 2, we jump up to 0 with R2. From 3, we jump up with 0 with R3, right? Et cetera, et cetera. Right? So the chain will either march forward or it will jump back to 0. Okay. Right. So we won't prove that this chain is transient. Something you can kind of see is because the probability of jumping forward just tends to 1 as the chain gets large. But for now, let's just show that there's no non-zero solution to our equation. So again, we're going to look at P. Right, so okay, I'll just write down the matrix P. So in this case, we have 0, 1, 2, 3. And then 0, 1, 2, 3, etc. So it's no longer a matrix, it's an infinite matrix. So the first column here is pretty easy. It's just 0. And maybe I'll ask you guys, so what should I put here in the first column according to our picture here? So there isn't like any math involved, it's just following the rule, just recognizing what happens. So what should we put in the first column? We know the first entry here is 0. I already put. What's 1, 0? What's the probability that we go from 1 to 0? R1, right? And what's the probability that we go from 2 to 0? R2, right? So R1, R2, R3, etc. Right? So that's what happens in the first column. And well, the second column, you can see that. Well, from 0 to 1, we go with probability 1, but let's just put this as Q1. Sorry, Q0, right? By definition, our Q0 is 1, right? And the rest are just 0. Right, so what about the next column? So I'll ask you guys again. So what's going to be? So what's the probability that we go from 0 to 2 in one step? 0, right? What's the probability that we go from 1 to 2 in one step? Q1, right? And then from 2 to 2, we can see that these are all just 0, right? Okay, and now we look at the next column. So maybe you already see a pattern here. So from 0 to 3 with probably 0, from 1 to 3 with probably 0, from 2 to 3 is going to be probably Q2, and then the rest are 0. Right? So maybe I'll just highlight the interesting part of the matrix. So the first column here, so I'll just highlight the non-zero entries here. It will be this one, and also this sum of this diagonal here, right? So these will just be the non-zero entries, and the rest are just going to be 0. So we have upper diagonal of Q0, Q1, Q2, and the first column is 0, R1, R2. Okay. So now, so we want to solve we want to solve the equation pi of p is equal to pi. Again, let's just look at the ith coordinate. Ith coordinate. Right? So of course, the ith coordinate of pi is just going to be pi. So now we just have to figure out what's the ith coordinate. Well, maybe not look at the ith. Let's just look at the first coordinate, the zeroth coordinate. Okay, so maybe I'll change it to 0. This is something that is precise. So pi of 0. And can you guys tell me what's on this side? What should we put on this side? What's the first column of the product between pi and p? Actually, not first column, first entry. Sorry, what? Right, exactly. Right. So it's a summation, right? Of well, the zeroth entry will be 0, so I goes from 1 to infinity of pi I ri, right? So any questions about this equality? Right. So think about, we're just doing the inner product between, let's say, pi 0, pi 1, pi 2, etc. Right, with this vector 0, r1, r2, etc. Right. If we do the product between these two things, we're going to get that sum. Right? So now let's call this equation number 1. Okay, so the second equation will just be for general I. So what kind of thing we're going to get for general I if we look at the pi? Yeah, question. Yeah.
So if we only focus on pi 0, I think the pi 0 has a very large probability that larger weight than 1.
Sure, yeah. So over here, we're not, so in general for these kind of things, we would just try to solve first non-zero solution first. We don't really require to be sum up to be equal to 1. And because you can, in the end, you can always just normalize, right? So you can add up all the entries and just divide by whatever solution you find to get a probability measure.
I mean, that if the pi 0 is greater than 1, and the sum of all pi entries will greater than 1.
Sure.
So it will not be
well, in general, but you can think about, so the entries of pi i's, they can, for example, if we sum up all the entries of pi, we get a number, let's say 10,000.
Yeah.
If we divide pi by 10,000, we're going to get back a probability measure. Right. So in general, this is not a problem unless the sum of the entries is infinity. Right. So that's like a general thing that we can think about. This is one of the ways we can think of. Yeah. So for now, we're only worrying about the equation. So we're not really worrying about whether if it's a probability measure, right? So in this case, we're trying to show there's just no non-zero solution. You'll see. So in this case, pi 0 actually, after we see that pi 0 actually can only be 0. So it cannot even be positive for this one. Okay. So now just by looking at this, we're going to get the first equation. So now let's look at I. So this is something you don't have to write out. So but it's pi I. So I'll ask you guys. So what's going to be the equation for I? So I know one side I'll have pi I. This is I is greater than equal to 1. So what's going to be on the other side? It's something simple, right? Because for all these columns, there's only one non-zero entry. So imagine if we have this inner product, but replace this one here by any column in the matrix, or by the ith column of the matrix. So it's almost. Yep. In this case, let's see. Let me double check here. So if we look at the ith entry, I think it should be pi I minus 1 times q I minus 1. Okay. Right. Well, it's because, let's say if we look at the third entry here. Oh, wait, yeah. If we look at the third entries here, and so this is Q2, and then with the thing we're going to multiply is also Q pi 2, right? Is it pi 2 or pi 3? Let's see. It should be pi 0, 1, 2. Maybe it's 3. Sorry, it's pi I. Wait. Let's see here. So I think in the notes I had pi I minus 1. Oh, sure. Yeah, sorry. Yes, it is pi 2. Yeah. because we're gonna, okay, maybe just example. So if we have like 0, 0, Q2, 0, 0, 0, right? So the only term that will be contributing will be this one, this one. This is in the third column, so it's I minus 1, I minus 1. Okay, so now we're just going to do some derivations with these two equations. The first thing we can do is let's just do a use inductive using 2 inductively. So well, that's right. So pi I, we know that is equal to pi I minus 1 times qi minus 1, right? Because this holds for any I, so let's apply it to this term. And then we're going to get this is equal to pi I minus 2 times qi minus 2 times qi minus 1, right? So here we're simply just replacing this term with this term here, just by the definition. And then we can see that we can repeat this in the end. We're going to get just a product. I goes from 1 to, sorry, j goes from 1 to I minus 1 of qj, this thing times pi 0, because we can replace, repeat, I should say, repeat this. Right? So we just keep on repeating, and then we're going to get this, we're going to get this. So now let me just write it out on the bottom. So this is pi I is equal to the product of j goes from 1 to I minus 1 of qj times pi 0. Right? So let's call this star. Okay. Now let's move to the next board. So questions so far while we're moving the board? Okay, so now what we're going to do is we're going to plug star into 1, okay? Because we have the pi I inside our first equation 1. So then what we're going to get is just going to be the summation I goes from 1 to infinity. Well, the pi appears there, so let's replace that with this product of j goes from 1 to I minus 1 of qj of pi 0. And we also have the ri is equal to ri is equal to pi 0. Right? So this is our new what we get after we plug in the star into the first equation number 1 there. Well, because 0 here it is something that is independent of any of the index, so let's just move it out. So maybe I'll move that afterwards. So I'll just write this. J goes from 1 to infinity. Sorry, I minus 1 of qj times ri. So let's make this block here. And then I have a pi 0 here, and I also have a pi 0 here. Okay. Right. So now we see that pi 0 appears on both sides. So now we can just make two quick observations. If pi 0 is 0, what can we say about the other entries of pi? The other entry will also be 0, right? From the star, right? From star, then pi I also must be 0. So it's not a non-zero solution. So pi is actually just going to be the 0, 0 solution, right? So essentially it says if we were looking for a non-zero solution, then the pi 0 cannot be 0. We have to assume that pi 0 is something that is strictly positive, right? Now, if pi 0, let's say, is strictly positive, we're going to get a contradiction. Let's call this double star. This equation double star. I'll just write it out and I'll ask you guys why. So double star shows, okay, maybe I'll write it a bit later. I'll ask you guys. So what can we say about this term here? Using the fact that we know So we know the summation of Ri is strictly less than 1, right? But what can we say about the product here? Oh, yeah, exactly. Yeah. So, okay, so maybe I'll just say this. So we know the product here is always going to be less than 1, right? Because of the QI is their number between 0 and 1. So if we multiply a bunch of these numbers, they'll be less than or equal to 1. Then the summation of this product with Ri, this is going to be less than or equal to just summation of I goes 1 to infinity of Ri. So this entire thing, I mean, is going to be less than this and it's strictly less than 1. Right? So now we see that there is a contradiction, right? So we show there is a number that is strictly less than 1 multiplied by pi 0 that is equal to pi 0, which is impossible, right? We shows that okay, so so some number, I'll just write some number that is strictly less than 1 multiplied by pi 0 is pi 0, right? But this is, we know if pi 0 is positive, then this is impossible. Right? So in the end, we show that there is no non-zero solution for this for our equation. So the only solution is the 0 solution for the end of this example. Okay, so any questions about this example? Okay, so maybe I'll write this step a little bit clearer. I think people are thinking that up. So I'll write it. So this is J, right? So think about this term. So the term here inside the bracket is less than or equal to the summation of I goes from 1 to infinity of Ri, which is strictly less than 1, right? So that's all. So this term here inside the bracket. Right? Oh, so some number strictly less than 1. Right? It's because this is strictly less than 1, right? Oh, strictly less than 1 times pi 0 equal to pi 0, right? It's the equal to pi 0, right? So this number here in the bracket is strictly less than 1. This multiplied by pi 0 is equal to pi 0, but that's impossible if pi 0 is positive, right? So that's the. I mean, well, pi 0 cannot be positive, it implies, right? This number is strictly less than 1. Okay, think about any positive number. So if you multiply by something that is strictly less than 1, you won't get it back, right? So no such positive number exists, right? So this implies pi 0 cannot be positive, right? So because this term here is strictly less than 1. Yeah, so right. So in this case, there's only the 0 solution for our equation. Pi p is equal to pi. Yep. Any other questions? Okay. All right. So far we look at the transient Markov chain, and then we can say transient Markov chain. And in this case, let's say what happens if the Markov chain is recurrent. So this finished the discussion about the transient Markov chain, which started in the first board. So in the second case, if given an irreducible, we always assume that it's recurrent Markov chain. So there are also 2 cases, right? So you can think about, they're either you can think, let's say, either there exists a station distribution or there exists only a non-zero solution of 2 pi of p is equal to pi, but pi is not a probability measure. So you can think about then when the chain is recurrent, then there will always going to be a non-zero solution to this equation, but then there are still two cases, right? Either pi can be turned into a probability measure, or pi cannot be a probability measure. Right? So next, I'll just let's see how much we have. 10 minutes. Okay. So example. Well, maybe I'll ask you guys. So can you guys think of an example that where there exists a non-zero solution to this equation, but pi is not a probability measure? So we already seen something similar that is today, that we have seen. Example. So there exists non-zero solution, but not probability measure. Okay. Exactly, right? So just take a simple symmetric random walk on Z. So in this case, it means P is a half. Right? And the exact calculation there holds if you just plug in P is equal to half. And our solution is going to be any constant then. Right? Just like before. So pi P is equal to pi, okay, because the chain extension is irreducible, the only solution it has only has the solution like before. The solution. Well, in this case, it's just going to be some constant C. Of course, there are also infinitely many ones, right? Because any constant C would work, even negative C would work, right? So, but then there's no way to turn this into a probability measure. Right? Okay, so this kind of motivates the definition between positive recurrent and no recurrent, right? Because as we see that even when the Markov chain is just recurrent, there's still possible for there to not be a stationary distribution. So now now here's the other definition. So so recall that X inside our space S is recurrent if following one of the definition is if the probability that Gx less than infinity, given that x0 is equal to x, so this is 1, right? So we know this just shows that then t of x is finite almost surely, right? So this implies, this means t of x is almost surely finite. And of course, if we have a random variable function that is almost surely finite, it doesn't mean its integral is still finite, right? So of course, from calculus, we can easily come up with some functions that they're almost really finite, but the integral is infinite. So that's what happens here. So I'll just write now, if the expectation of Tx given our starting point is to x, this is infinite, the x is null recurrent. Oops, did I forget to switch the board? Let me double check. I did? Did I? Okay, I did. Let me highlight it with a color. is no recurrent. And on the other hand, of course, if it's strictly less than infinity, then X is positive recurrent. Okay. Now let me put the definition up. Okay, I'll erase this part of the word. Okay. So next, I'm just going to make some remarks. You can also think about their actually theorems. Well, the first is a positive recurrent Markov chain is just similar, or you can think about exactly pretty much the same as finite state Markov chain, right? Positive. Okay, maybe let's start with some facts. Positive recurrence is a class property. Okay, let's write this first. Right. So this means E if X is positive current, recurrent, and X communicates with Y, then Y is also positive recurrent. It's something maybe we won't prove, but so essentially it says if we work with irreducible Markov chains, it makes sense to say whether the chain is positive recurrent or not, right? Because it's a class property. Okay, and also positive recurrent Markov chain is similar to finite state space Markov chain, right? So they essentially behave very similar, right? So some fact, suppose let's say Xn is a Markov chain. Let's say it's a irreducible aperiodic positive recurrent Markov chain. And there are just a bunch of a nice property from before, they all hold, right? So the first one, you can think about the limit as n goes to infinity of Pn of X and Y. Okay, maybe I should say there exists there first. Let's not say this. So first I should say there exists a unique stationary distribution. Let's call this pi. So we have the existence, we have the uniqueness, and we also have the convergence. The limit as n goes to infinity of Pn of X and Y is equal to pi of Y, where X and Y are just elements inside this inside the state space. And number three, again, we also have the formula, which is given that the expectation that Tx expectation of Tx, given that x0 is little x, right? So because we know the Markov chain is positive recurrent, so this expectation is finite, and we can actually say that it's equal to 1 over pi of x. Right? So essentially, for positive recurrent Markov chain, it's similar to finite state space Markov chain. Okay. So I guess we're almost up time. And so in the end, maybe I'll just state a simple fact. Well, the proof, I guess, is not too simple, right? So which is another fact, which is any finite space Markov chain is positive recurrent. I don't think I know a simple proof for this. I think there might be some argument. I think we should have all the necessary knowledge to prove this, but the proof is a little bit long. So I'll just simply say this as a fact. Okay. So you can almost like treat positive recurrent Markov chain as a finite state Markov. Of course, they're a little bit different calculation-wise. Okay. So any questions for today? Questions? Sure. Oh, sorry. Well, let's see. Okay, yeah. I guess assume it's like irreducible, because or else it doesn't make sense to say a Markov chain is positive recurrent. But yeah. Okay. That's a good point. Yes. Irreducible Markov chain. Right. Because initially the definition of recurrent, transient, positive, or no recurrent, they were initially only defined for each individual states. And then to say whether a Markov chain is recurrent or not, we kind of have to implicitly assume that they're irreducible, or else the definition doesn't quite make sense. Yes, that's a good remark. Yes. Okay, I guess this is it for today, and so I hope you guys have a nice break next week. So I'll see you guys in the week after.